be starting to focus on machine learning and how statistics is important for machine learning. And today's our focus is going to be on regression and predictions. Yeah, I'm super excited. I hope you are too. Before we start, let's me start by thanking our volunteers. They have been key in putting together this whole entire webinar in a very timely fashion. Today in this chat, you have me, Sneha. We also have Rishika, Aryan, Sahana, and Samya today with us, and they'll be taking care of the Q&A and chat session for us. And a huge shout out to our sponsor, the Home Depot, as well. They have been a wonderful support to our community in putting together so many events that is very educational. And yes, and I also want to share links to all the resources that we have so far. So if you have missed or want to recap any of our previous webinar series, you can check out them in this slide. We have links to our GitHub code, and we also have YouTube links in this slide. And as I said, we are starting with machine learning and how statistics is important in machine learning today. I also want to refer you to the past series, Introduction to Machine Learning and Advanced ML series. So if you're new or if you're a beginner, I think this will give you a holistic learning about ML models. So make sure to check them out as well. And about today, as I said earlier, we are focusing on regression and predictions. Please note that this webinar is going to be in R, and the topics that we will cover today are linear regression, and then we'll jump into real world example, factor variables, regression diagnostics, and we'll end it with polynomial and spline regression. And our speaker for the day is Madhurima Nath. I'm excited to introduce you all to her. She holds a master's in quantum physics from IIT Delhi, India, and a PhD in statistical physics from Virginia Tech. In academia, her focus was computational modeling of dynamic systems, predicting epidemic outbreaks, and analyzing interactive magnetic systems. She was engaged in multiple cross-disciplinary machine learning projects as well. She was also a physics instructor and participated in many outreach programs. Currently, she is a data scientist at a technology-focused consulting firm where she leverages cloud-based platforms like AWS, Azure, and Google Cloud Platform for business solutions. And she has put together for us a very wonderful presentation packed with so much information. I'm excited about it. Madhurima, thank you for joining us today. And before I hand it over to you, I just want to let everyone know that there is no Google Colab notebook today. We have a HTML page of an R notebook. So link to that would be here, and Samya will share the same link on the chat. Please download it and view it in your browser. And if you want further instructions, Madhurima will be providing that. Madhurima, you can take it away from here.
Thank you, Sneha, for that wonderful introduction. And hello, everyone. I'm going to start sharing my screen. And I saw a couple of messages saying there are some issues, and I will address them as to why that is happening. And let me know when you can see my screen.
Oh, yes, we can.
Okay, perfect. So if you go to this link and you hit download, you may be seeing something like this. And that's totally okay. It's just because the file is a little big. So just right click on your browser and hit save as, and just save the HTML document. And once you have done that, if you open the file, you should see a nicer and cleaner HTML document. And I'll pause here so that everyone has time to do this. And please do a thumbs up in the chat or thumbs down if you're still having trouble, and I can go over it again. Is it working, not working?
I think you're all set.
Okay.
Oh, there are a few. If you don't mind repeating that
Yeah,
again.
yeah,
Yep.
I can definitely repeat that. So if you click on the link and you see a file like this, don't be scared. It's all good. Just right click on the browser and do a save as, and save the file as HTML document. And once you have done that, just open the file again, and you should see this. It should appear in a nicer format.
Awesome. I think we can continue, Madhurima.
Okay, great. Awesome. So there should be a link to the slides as well. I will be using, I'll be using slides to begin with, and then I will jump over to the notebook. So if you hit this link, you should be able to download a PDF version of the slides. So let us know when you're all ready, and I will start. I'll give it another minute, and then I'll start. Okay, so as Sneha mentioned, we will be going over regression and prediction. Again, thank you, Sneha, for the introduction. And I'm really excited to be here. And let's hope we learn a little bit about regression and how statistics is present in regression. So today I'll be giving a brief overview about linear regression, and then going over simple linear regression and multiple linear regression. And then we'll go on over to the R notebook to do a hands-on real world example using the methods that we learned. We'll pause a little bit for Q&A after our real world example. And after the break, we will continue with factor variables, outliers, correlated errors, influential values, and few other points which are very important to remember when we are doing regression analysis, such as multicollinearity, bias variance trade-off, and how to tackle that using ridge and lasso regression. And lastly, I'll be going over polynomial and spline regression. Again, if you have any questions, there is a Q&A chat box. Please feel free to put your questions out there. So let's get started. Linear regression is the basic first tool that we all do in machine learning. So what it does is it has two variables. One is the dependent variable y, and the predictor variable, which are called predictors, are x. Um, Now, linear regression establishes a linear relationship between X and Y. So a little bit of math in this. So if we have n data points and there is X represented in vector form, so then we can say that this equation yi equals beta 1 x1, beta 2 x2, and so on and so forth, plus this epsilon I, and I'll tell what these are, represents mathematically what a linear regression is. So again, yi are the points which are the response variable. Betas are the coefficients that we try to estimate in our model. X's are the predictors or the independent variables, and epsilon i's are the errors that we get. And and this can be represented in a matrix notation as well. For those who are aware of matrix notations, it is just big Y matrix equal to X and then beta matrix plus epsilon matrix. It's just a much more, when we go to higher dimensions, how we would write this is in matrix notations. And the best fitted model is the one which reduces this error, which is the epsilon. And for linear regression, we generally work with the least squared error. So I'll go over to linear regression, the assumptions. And again, just reminding, please feel free to type any questions if you have in our chat. Now, there are two very important assumptions when we are doing linear regression. One is the errors or the residuals that I talked about, that is the epsilons. We assume that they are identically and independently distributed. And the errors are, again, normally distributed with a mean of 0 and equal variance, which is unknown, and we call that homoscedasticity. And I will go over how to check whether our residuals are normally distributed or not, whether they have, what is the nature of the residuals before we do any linear regression. And I will cover these later, but these are the two most important assumptions of linear regression on which the modeling is based. So jumping over to the two regressions that we always work with, one is the simple linear regression and the multiple linear regression. The simple linear regression is the most easiest one, and I'm sure all of you have done this in high school. It's just drawing a straight line when you have some X values and Y values. So it is just a simple straight line with the regression coefficients are the intercept and the slope. Mathematically, again, we can just represent this as yi equal to beta 0, and which is the intercept, and beta 1 xi, and beta 1 is the slope. And again, there will be the error terms. Now, what our model does is calculates what is the good estimate for beta 0 and beta 1. And how it does that is it just tries to get to these two equations here, which are written down. And what these equations mean. So to put it in context, beta 0 hat, why I represented it as a hat is because I am trying to estimate these values from my model, because I am only given x's and I'm trying to estimate what my betas would be. So this is given by y bar minus beta 1 x bar. And the bars here represent the mean values, which is the mean value of all the x's and mean value of all the y's. Similarly, we can get the value for beta 1 using this big formula over here. It just looks big, but it is just very simple. It's just the values of x's, and we would need the mean value of all the x's, the values of all the y's, and the mean value for all the y's. Once we use that, we can get an estimate for beta 1 and beta 0. Now, what does this physically tell us? What is the interpretation? It's all good mathematically, but what does it physically tell us? So beta 0, or the intercept, tells us what is the estimated equation at x equal to 0 when the predictor value is 0. So what is my y value, or what is the response variable at x equal to 0? And beta 1 gives us the amount by which the mean response vary whenever there is a unit increase in x. So whenever my x increases in 1 unit, how does y increase or decrease? When x decreases, how does y decrease? So beta 1 tells us that, gives us that information. Now, multiple linear regression is a more generalized version of the simple linear regression. And it just uses more than one predictor. Here, X is what I was using as one single predictor, but for multiple, it would be 2, 3, 4, and so on and so forth. So you can imagine it would be very difficult to write it down in just a simple equation. And hence, matrices come in very, very handy. And that is why we use matrix notations, and writing it down in a matrix notation just appears as a very simple equation. And I would say generally all real life problems that we solve involve multiple linear regression, and involves multiple predictors. It's very rare that we would only work with one single predictor as a simple linear regression. Okay, so now we will be moving on to the real world example. And for that, I will be moving to the R notebook, and I will give everyone a little bit of time to go into the R notebook. And please give us a thumbs up when you can see the notebook, and to the section which says real world example using regression. I'll give it a minute before I start.
Hey, Madhurima, sorry to jump in here.
No.
So when you say the R notebook, it is the HTML file that
The
you
HTML
downloaded.
file, yes.
I just
My
want to
bad,
make sure
yes.
everybody.
Yes, the HTML file that we downloaded. And
Yes.
thank you, Sneha, for that. Okay, so let's move on. So we are going to use this data set, which is or represent in R, which is the New York air quality. You can also download the data from Kaggle if you click on this link. And if I click on the link, and let me move my Zoom screen around, just give me 1 second. Okay, yeah. So You can download this from Kaggle if you want to work on your side on Python or Jupyter. This file works fine. If you are in R, you don't have to download it. It's already present in the R environment. Okay, so the data has 6 variables. And for our purposes, we are going to use the attribute ozone as our target variable, and all the rest 5 of them, as solar, are wind, temperature, month, and day as our predictors. Now in R, just a little bit of background, we use the LM function to create a linear model, and we use the predict function to do some kind of prediction. So it is similar to how we do in Python. It's just the names are different. So I thought I'd just give an overview of what we are going to use. So again, once you're in R, it's just, we can just load the data by just calling the data, and it comes out in a data frame similar to how we would do in Python. Again, when we do a head, we can see how the data looks like, what is the variable type. We see there is integers as well as double. We see there are some missing values, and I'll address all of that. Again, just just installing a few libraries that I would need to do the analysis. And now to do some initial exploratory analysis, as we start for all machine learning problems, check if there are missing values in our data set. And once we apply this function, we can see, yes, there are indeed some missing values in the ozone and the solar.r columns, but the rest of them are pretty good with missing values. So there are no missing values there. So what I did was I imputed the missing values in ozone and solar radiation by replacing it with the monthly average. And this is just a few lines of code to replace that. And with the monthly average, and once I do that, I see that there are no missing values present, and it has been imputed with the monthly average. So now that my data is all nice and clean, I will go on to apply the simple linear regression. I'll start with the simple linear regression, and I will take the attribute temperature as my one predictor to predict the behavior of the target variable, which is ozone. Again, in simple linear regression, we use only one predictor. So now we just do assign the temperature column to my X, the ozone column to my Y, and I call simple model, use this function to build out my simple linear regression model. So once I do that, I get the values for my intercept and my slope. So now I want to see what this visually looks like, because I don't know what minus 116.372 intercept means with respect to the data. So I do that, and the dots here show the data points, and the blue line here shows what came out of my simple model. That is the line with the intercept value of minus 116 and the slope of 2.019. So next comes the question is, how do I know how good or bad this line is with respect to my data? Is it a good model? How do I evaluate what this is. Where can I get that information? So we can get that very easily in R by just calling this function called summary and calling that function on the model itself. And it spits out a bunch of these text. And it's a lot of information, and I will go over them one by one. So bear with me here. It's going to be a lot of talking. So the first output that comes out is just says call. It is nothing big. It just tells you what was the formula that was used to fit the data. So it says LM, which is the linear model, and the formula that was used was just y with respect to x. And here x just was one variable, which is the temperature, and y was the ozone. Next section is called residuals. And residuals is the difference between the actual observed response variable, that is actual y, versus the y that my model LM predicted using this function or using this formula. So what is the difference between that? And this section is broken down into 5 points. Minimum, first Q means the first quantile, median, third quantile, and the maximum value. So it's actually telling me how are these residuals distributed. And again, as I said, I will tell you, I'll show you how, if I plot these residuals, how they look like, and we can kind of relate it to the assumptions in some time. The next section is called the coefficients. Now, the coefficients is what we are looking for. That tells you what my beta values were. That is what I wanted an estimate for. So here it tells me what is the estimate for my intercept, what is the estimated slope value, it is beta 1. And it also tells me what is the standard error in doing that estimation. It is just the standard deviation of these estimated values. The next is the t-value. Now, the t-value is a measure of how many standard deviations away from 0 is my actual estimate. So it means if I just multiply t-value times my standard deviation result, I will get back the value of my estimate. So how far away from 0 is my estimated coefficients? It will tell you those values for the coefficients that I'm trying to get from my model. So the further away from 0 it is, the better my model is. Why? Because the further away from 0 is, it rejects the null hypothesis. The null hypothesis is that there is no relationship between x and y. So they are completely independent of each other, and there does not exist any relationship. So this whole model I'm trying to do will not work if there is no relationship. So if it is away from 0, the further away from 0, the better it is, because there I can prove that yes, there exists a relationship between these predictors and my response variable. The next section is something which is written as PR greater than T. This again is very simple to understand. This just tells you what is the probability of observing any value which is greater than or equal to T. And it is very, very small. So again, the smaller these values are, it is more unlikely that X and Y are unrelated. All of these values actually tells us that yes, there is a relationship between X and Y. And these are just different ways of kind of reiterating the fact that yes, X and Y are related and they are linearly related. Now, the last section, sorry, the next one is this 3 stars that you see, which just tells you the significant codes. So 3 stars represent 0, which means that I am very confident about my result, that this value that I have got is correct. That is, there exists a relationship between X and Y. So again, as I said, these are just different ways of confirming the same thing, that there is a relationship between X and Y. Now, the last chunk of this is the residual standard error. Now, the residual standard error measures the quality of your linear regression fit. So it's the average amount that the response will deviate from the true regression line. So if there was a true and absolute truth relationship between X and Y, so how well does my model do in predicting that exact relationship is what is the error that my model is doing in getting to that true value. The next is the multiple R squared and the adjusted R squared. So these are related to the R squared value. And R squared basically it's a statistic that provides a measure of, again, how well my model is doing. It ranges between 0 and 1. So the closer to 1 the R squared is, the better my model is doing. Now, this multiple R squared value will always increase the more predictor we take into account. But that will lead into something called overfitting, which I will address in some time, again, in the next section. So we can use something called adjusted R squared, which takes into account that, yes, I have like 3 different predictors, and maybe I should not just assume that it is doing good just because I am adding more and more variables in my model. So it's just, again, a way of doing model evaluation. The next is the F statistic. Now, F statistic tells me if there is a relationship between X and Y being tested. So generally, the further away from 1 it is, the stronger the relationship is. So, and the less the p-value is, it just tells you, yes, I can confidently reject my null hypothesis of saying that there exists no relationship between X and Y. So again, I know it sounds very repetitive because all of these are trying to tell you, yes, there exists a relationship between X and Y, and that is what we have been trying to figure out from our model. But these are different ways of checking how well my model is doing, how well my estimates are, what is the error, and what is the distribution of residuals, and is just reiterating and confirming our assumptions that we started with when we did this linear regression. And all of these is just written down over in the notebook for you to refer later on. And again, if you have any questions, feel free to write it down in the Q&A chat so that we can address that later. Okay, so the next section tells you, again, the same thing that I showed before. It's a relationship, it's a plot between X, which is temperature in this case, and Y, which is ozone. And the dots here represent the data, and the blue line tells you the line I obtained from the simple linear model. The gray shaded area around here, it will tells us how confident we are in our uh, model. So it gives you it gives us a 95% confidence interval, which means it is the estimated, uh, like if I perform this experiment 100 times, then out of that 95 times, the line will lie in this gray line area. There is still some variability in what would be the outcome of my linear model, and that variability is represented by that gray line. Now, I was telling you we'll talk about the residuals, and we'll go into if it is matching with our assumptions with the linear regression, and how we can do that are very simple three different steps. One is we can check for the normal distribution. So if you remember, I said the assumptions of linear regression are that the residuals are normally distributed. So we can check that very easily doing a histogram. We can check that by doing a normal QQ plot. And we can check that also by doing a standardized residual chart. Standard residual is just residuals divided by the standard deviation. So this chart here shows the histogram of the residuals. So I just plotted the residuals and the histogram for it. So if it is normally distributed, this would be a Gaussian or a bell-shaped curve. So we can see that there are a few which does not lie underneath. So it has a little bit of tail. So which means there are some residuals which are kind of lying outside the majority of our data points, and we will call them as outliers. We'll revisit this topic again. Similarly, if we do a normal QQ plot of the residuals, if everything lies on this dotted line here, then we can definitely say, yes, they are normally distributed. They are identically and independently distributed with a mean of 0. But again, we see that there are a few in this data set which do not lie on this point, but majority of it lies on here. Similarly, if we do a residual chart, it should, if everything was normally distributed, everything was identically and independently distributed with a mean of 0, it should lie around the 0 line and within this red lines, which is the threshold. But in this data set, there are a few which kind of goes beyond, and this is what we will call as outliers. We can also see that there are no patterns in this residuals. Like we can't really say if we plot the residuals, we see some kind of a straight line or polynomial line or something like that. So which is good. We want the residuals to be random in nature. So all of these are telling us what is the distribution of the residuals and if our assumptions of linear regression is being satisfied or not, which means that is it a good thing that we are applying linear regression on the data set that we have got? So this is again related to what model we are selecting, whether it's a good model for our data or not. And all of these kind of tells us, yes, we have selected a good model, or no, we have done some mistake. We should select some other model because it either does not satisfy the assumptions of the model, or there are too many outliers, or we are seeing something different which should not be. So these are just, again, number of checks, any of which will tell you if we are satisfying all of these things. Next, we will move on to the multiple regression on the data. I'm going to use the same data set, But instead of now just using the temperature, I'm going to use all of the variables. Let me give you a peek at the data set again. So we have all of these variables. Ozone is again going to be my target, but now I am going to include solar radiation, wind, temperature, month, and day, all of these 5 in my model, because I want to do a multiple regression. So I include all of this as my X variables, and same as before, I have ozone as my Y variable, and I call my linear model again. I say I want to do multiple regression. I still want a relationship between X and Y. I want my data to be the air quality data that I have, and let's see what the model outputs. So I call a summary on this to see how well my model has done. And similar to what I explained before, this will tell you what was the formula that is used. The next section tells you the distribution of the residuals. And then now I get all the estimated coefficients for the intercept, the solar radiation, wind, temperature, month, and day. And these are all the estimates that I have gotten, along with all the other things that I told: standard error, t-value, residual error, r squared, so on and so forth. So if you notice, my r square has increased for simple. So here we see that the r squared is 0.05. And going back to simple linear regression, my r squared was 0.4. So as I said, r squared increases if I include more and more predictors, but we have to be careful about overfitting, which I will talk in coming few slides. So that's it's I don't have a plot for multiple regression because it's again not a straight line. So it's in now a much higher dimension space. So it's a little bit tricky to draw that, but we can definitely do that by fixing all the other variables and trying to do a plot of one of the predictors if we want to see the relationship. But again, it would again become a version of the simple linear model. So I'll pause here for any Q&A, any questions that you have. I'll put it over to Sneha for any
Thank you,
questions.
Madhurima. That is a wonderful presentation. Thank you for taking
Thank you.
us through linear regression and multiple regression so far. We do have some interesting questions that I thought
Sure.
you would be good at answering. I mean, good to answer. Sorry about that. So
I'll try my best.
So the first one is on residual standard errors. Is there an optimal standard error that we can expect in a model?
Ideally, you would want your error to be 0. So the closer to 0 it is, the better it is. We don't want, so as we can see, this one is very high value. We do not want a very high error because that will impact how my model is working or what is the accuracy of my model. So the closer to 0 it is, because I want, as I said, if we go back to the assumptions, give me 1 second. Yes, we want our errors to be normally distributed around the mean of 0. So the closer to 0 it is, the better my model is going to perform.
And there is another question on residual standard error. What is the degree of freedom that accompanies it? Can you explain a little on that?
Yeah, so it's going to be a little bit tricky, but sure, I'll try my best. So
the simplest answer possible. Yeah.
So degrees of error is actually how many data points you have. So and that -1, because 1 is what think of it this way: you fix 1 and you are kind of trying to estimate everything else with respect to that. So degrees of error, degrees of freedom is basically how many of those unknowns you have when you're trying to estimate that one value. So that's related to it, would be a simplest way of answering that.
Awesome. Yes, that sums it up. I hope it answered your question, Jasmine. The next question is by Alex. How much can residuals deviate from a normal distribution before it is problematic to the model?
That's a very good question. And I think it would depend on the data itself, as well as there is a threshold that we can always either define, or it's defined from like the best threshold is defined by the model itself.
Mm-hmm.
So you would want your residuals to kind of stay within that. And I will talk a little bit more about residuals and what is the threshold when I'm talking about regression diagnostics. And there are things like cook distance and DFFIS distance, which also helps to calculate that. And I will go over that in detail after this section. But there is a threshold, like again, ideally you would want it close to 0, but again, there are measures like cook distance, and we would want it to be within that threshold, like within that threshold that you have defined.
Yes. So basically, we want it as close to perfection, but it's not going to be that, because it's data, and data is always messy, and there's going to be outliers and everything. Yep.
Yes. So if let's say now I have 1, 2, 3, 4, 5, like 5 is going kind of above the threshold. If I would have, so 5 out of 150 is not that bad, but if I would have like 100 out of 150, then yes, then linear model is not going to work for that data set, just because it does not adhere to the assumptions that we started with.
Yes.
So I hope that makes sense.
Yes, it does. Thank you so much for answering that. The other question is, if the p-value is like very less than 0.0001, what does that mean, or what can we do about it, is one of the questions.
So generally, whenever we define a hypothesis, we always say, okay, I will accept or reject this hypothesis based on, a certain p-value. So it is up to us to define that. The best practice is always 5%, like whenever it is 5%. Highly, like whenever it is a very, very, very small value, like you mentioned, that just means that you are very confident in rejecting your null hypothesis. So in this case, our null hypothesis would be there is no relationship between X and Y. So if it is 0.00001, then you are like, okay, it's great. I can 100% with almost very much percent confidence say that there is a relationship between X and Y, and my null hypothesis is wrong.
Yes. Sounds good. Yeah, that is all the question we have for now. And thank you for answering. I think you solved all the questions. We can move on to the next section.
Great. Okay, so for the next section, I'm going to go back to the slides again, and please let me know if you can see my slides. And I'll give it a minute so that everybody has time to jump on. Great. So let's start with factor variables. So factor variables are categorical variables. So those can be both numeric and character variables that can be made into factors. Now, month in our data set, if you remember, is a factor variable. And you saw that numbered as 1, 2, 3, 4, but it is actually telling us which month it was. So it could also be named as, January, February. So those are kind of the categorical variables, which are factor variables in linear regression. And there is something called an ordered factor variable, which is when these categories have a particular order, and we want to use that order to perform the comparisons. And we don't want it to be random, like some random numbers that exist. So we want that order to exist when we are building our model. So there are very simple ways to handle factor variables, and I'm sure all of you have heard about one-hot encoding and dummy variables. So it's just a way to handle categorical variables. And dummy variables is just you encode it into 0 or 1, and it creates k-1 variables for k categories. So for example, let's stick to the month example. So if January is month, so then whenever there is January in our data set, we'll label it as 1, and everything else is 0. Again, we'll start with, so we'll add another column which says whether it's February or not. So then if it is February, we will add 1 for February and everything else is 0, and so on and so forth. So that's how it creates k-1 additional variables. One-hot encoding also does 0 or 1, but now it creates k variables. Oops, my bad. Sorry. Yeah, it creates k categories for k variables, because now I have it. Think of it as becoming like matrix, where January is 1, anything that is not January is 0. And similarly, I would have February, then I will have March, and this kind of matrix will increase, and it will be either 0 or 1. So that's how I can assign these in my model. Reference coding is another way to handle factor variables, and that is when I have identified like a reference value, and I want to compare all the other values with that reference value. For example, I can just do January as 1 and everything else as, 1, 2, 3, 4. So I'm going to just add 1 more to that. Or I can have another variable where I want to compare it to the mean value of all the other existing categorical variables. So it can be decided based on the data or how you want to define it. So a cool thing about R is you don't have to, you can specify in R how do you want to encode it, but R automatically tries to encode all these categorical variables into factor variables, and you explicitly don't have to do it if you don't want to. So again, feel free to jump in questions in the chat. And regression diagnostics is the one I'll move next to, and I'll start with the outliers. So outliers are basically the observation which has a response value that is different from the ones we have predicted. So if you remember the charts that we discussed, there was this line, that simple model line that I had between temperature and ozone. And there were some data points, which I have highlighted here in red, which are completely off the chart of this line. So these are the points which I would call as outliers, because they do not, if I want to kind of predict what my values would be for these, it will be very difficult to predict it from this blue line. Similarly, I was mentioning about the histogram. If you remember, it had a small tail, and that was because there are some outliers which are present here in the histogram. And this is another way of detecting the outliers. Similarly, as I was going through QQ-plot, I mentioned there are a few data points which are just off this line that is here. And those are the ones which are the outliers. And just so that everybody knows and not to get confused with anything, these numbers which says 30, 62, 117, these are just the number, like the 30th data point, the 62nd data point. So it has no significant meaning other than just saying which data point it is. So these numbers have no other meaning other than that. So all of these are ways that we can use to identify outliers and how bad are those outliers with related to the model that we have got. Similarly, there is another one, which are the influential values. And these are any data point which kind of has an effect on my regression analysis or has an effect on the predicted outcomes that I'm having. It can affect the coefficients that I have estimated. And linear regression is very, very sensitive to outliers and this influential values. So we have to be very careful and identify these, how many of these are there and what to do with them. So as I was mentioning in the Q&A session, there are two very prevalent methods to identify this. One is the difference in fits. That is what I was mentioning as the DF fits. And another one is the Cook distance. So the larger these difference in fits or the Cook distance is, the stronger your influence is. That means they are going to kind of impact and affect your regression results. They're going to affect the estimated coefficients, and they're going to impact the model by itself. So both these DF fits and Cook distance work kind of on the same principle, and that is you delete one observation at a time and then refit the regression model with that observation subtracted from your n data point, and then compare the results with the original data point where you had all the n observations and see how much that data point has influenced your analysis, and do it for all the n. So this is what Cook distance and DF fits does. It takes one observation. It first starts with the entire data set and then draws, let's say, a line, just for the sake of simplicity. I'm doing a simple linear model. I'm drawing a line with n data points. And then I'm going to delete one observation and then draw the line again, and then compare how different or similar this line is. Then remove a second data point and do this again and again and see what is the result, or which are the points which is going to influence my result the most. So I worked with the same data set, and this is the plot of how the DF fits and the Cook's distance looks for my data. So if this is, I have a threshold value, and anything that lies within the threshold value is good, but anything beyond that, so all these data points like 30th, 60th, 117, this is hidden behind that, 121, all of these data points are kind of, they're potential influential values which can have impact on my linear model. Similarly, you can see all of these data points also come out in the Cook's distance as well. And all of these have the potential to impact the result of my regression. And again, as I mentioned, the closer to zero, the perfect the model is. So the last of the regression diagnostics is the correlated errors. And again, going back to the assumptions of linear regression is that all our residuals have to be identically independent, which means they have to be uncorrelated. If a correlation exists, that means that there is some information that exists in our data that the model has not taken into account. And that is why that information is now present in the residuals. So the easiest method to check that would be just to plot the residuals and see if there is any trend or not. Like this red line here is kind of trying to see if there is any relation like that, but I don't think there is, because it's the more random these residuals are distributed, the better it is. So you want your residuals to be randomly distributed. So we have to be very careful about correlated errors. So again, next points are very important to remember. One is multicollinearity, and the second is the bias variance trade-off. Now, multicollinearity is very common when we are doing any kind of regression analysis. And multicollinearity has a huge impact on model performance. So we have to definitely make sure that we are not dealing with a multicollinear scenario. So multicollinearity is when two or more predictors in our regression models are any way related to each other. For example, in our data set, let's say if temperature and solar radiation are highly correlated, then that is going to have a significant impact on our prediction. And we do not want that. We want all our predictors to be uncorrelated with each other. So the best way to check for multicollinearity is to calculate the variance inflation factor, or VIF. And anytime we have a large VIF, that's a concern. We have to get rid of the multicollinearity, and maybe we get rid of one of the predictors, which is highly correlated with another predictor, is one way to do it. And that way it will have a better impact on our model. Similarly, bias variance trade-off is something we need to take care of. That is underfitting and overfitting. So bias is underfitting. That is when you have assumed a very simple model to work, and you are not detecting the relationship that is present in the data. You have assumed that, okay, a very simple model is going to work. So let's say instead of a multiple linear regression, which would be the correct model, you are just working with a simple linear regression and one predictor. So that would be underfitting. And the error that comes from this incorrect assumption is what we call as bias. Variance is just the opposite extreme of that. When you have overfitted your model with supplying 10 different predictors instead of 5. So what will happen is the model will try to match even the noise that comes in, or even the smallest fluctuation, and that will impact the model performance whenever a new data set is coming in and you are trying to predict what is happening, because it won't be able to do that because it is so much more focused on the data that you had used to train the model. So the good way to get rid of overfitting and underfitting is doing a regularization, especially overfitting is doing regularization. And what it does is it kind of constrains or assigns a penalty whenever you're adding more and more predictors. So as I said, we will always have some kind of error in our, I mean, the ideal situation is we have no errors, but we will have some kind of error. And that error comes due to the variance and the bias part, as well as the epsilon, which is already present, the residual. So the ideal model would be the minimum error, where that is, if we have least amount of variance, least amount of bias, and least amount of epsilon. So to achieve that, there has to be a balance between how well we are fitting the model. Like, are we using too many predictors versus are we using very less predictors? So that's where the trade-off comes in. So till now, the example that I showed, I was using all the predictors. That means my penalty parameter, which is traditionally denoted by lambda, was equal to 0. I did not have any parameters which was saying, okay, penalize, wind term just because it is probably adding some kind of overfitness. So I was not doing that. So I was using all the predictors to get to my response variable. So opposite to that would be, I have a null model with no predictors. That would mean my lambda or the penalty term is infinite. So it makes everything, all the predictors go to 0. So that is also not what we want. So we want to keep somewhere in between, and we want to reduce the overfitting. So there are two ways to kind of do regularization, and one is the ridge regression and one is the lasso regression. So ridge regression is known as the L2 regularization, and lasso is the L1 regularization, and both of them are kind of very similar to each other, and I'll walk through what these two actually mean. So for ridge regression, again, it is a little bit of math, but it's very simple. So this big part within this parenthesis is the equation for linear regression. So this is what we have been trying to fit. This is the y, this is the betas, and we are trying to fit these values. So the additional term that comes in for regularization techniques is this lambda term, which is associated with my betas, because betas are the ones which we are trying to estimate. So what ridge regression does is it assigns a lambda with each beta squared term. So if you bring in more and more predictors, that is more and more betas, this term is going to increase, hence this side of the equation is going to increase, but ideally we want that not to happen. We want all of this to minimize, because we want the least error value. So this is what mathematically it does in behind the screen. Just wanted to give you a flavor. And in lasso, what it does, it just takes the absolute value of beta. Unlike ridge, where it squares the betas, this one just takes the magnitude. So that is the basic difference between lasso and ridge. But the nice thing about lasso regression is it has a possibility to shrink one of the coefficients to exactly 0. So it not only reduces the impact of those coefficients, but it can make it absolutely to 0. So the nice thing about that is we can do some kind of variable selection. We can say, okay, this variable is more important. in our model, and it leads to sparse models, which is not really possible in ridge regression. It doesn't force all the coefficients to go to zero, but it reduces the value. So this is just a table that I thought would be very helpful in understanding what I was saying. So again, going back to the example that we had, the data set. So these were my predictors for the ozone layer. And the column where I say multiple is the result that I got from doing the multiple regression. So these are the value of my intercept, and this is the estimates of each of these predictors. So when I do a ridge regression, I see that these values have decreased, but it has not for the month, but it has, most of them has decreased. But when I do a lasso, I see that month has gone down to zero. So this is what lasso does. It tells you that month is probably not, we're probably overfitting it with the month here. So maybe making it zero will give me a better result. And it also reduces all the other coefficients. And I have this done on the notebook, and I'm going to shift back to the notebook just to show how I obtained this. And I'll give you guys a minute to move back to the notebook as well. And go to the section of ridge and lasso regression. Notebook, sorry, the HTML document. So this is just an example of how I would do a ridge regression in R. There are similar techniques in Python as well. So for specifically in R, we can use this function called glmnet. And what it does is it looks it looks within, I have specified a range of lambda for it to look in, and it will select that value of lambda for which the mean squared error is the minimum. And this is the plot that shows what happens. So this is the mean squared error, and it's plotting the log of the lambda, or the tuning parameter value. And this is showing us that the minimum of lambda value lies in somewhere in this range. And that is what is the optimal lambda that my model is, that the ridge regression model is going to use. So in this case, it is somewhere around 4, like 3.98 or something. So now I can put this lambda in my model, and these are the results that I showed you in the table earlier. So that is what it does. Similarly, for lasso, I can do the same thing. And again, look for what is the optimal lambda value for which my mean standard error would be minimum. And it comes out to be 0.05. So I plug in that in my model, and I get back these coefficients. Just as an FYI here, dot, this is just an R output thing. This dot is basically means that this coefficient has gone down to 0. So this is how we would do a lasso and or a ridge regression on the same data set that I was working with. Okay, so now we'll move on to the next and the last section, which is the polynomial and spline regression. And start with polynomial, it is just trying to fit a polynomial relationship with x and y, like the response variable y and the independent variable x, but I'm trying to plot a polynomial relationship. Now, again, just a line of math, it just means that instead of beta 0, beta 1x, beta 2x, which we had in multiple regression, I'm going to have x squared, x cubed, x fourth for quartic, and so on and so forth. Now, you might wonder why I'm still calling it linear regression, even though I have like higher powers in x, and that is because the higher powers are in x and not in the coefficients beta. So it is still a linear regression because linear regression, it is still linear in the coefficients beta and y. And we are not doing powers of beta, we are just doing powers of x. I just want that to be clear to everyone because it was confusing to me when I first started learning it. So a word of caution for polynomial regression, similar to what I said about r squared getting higher just as we start adding more and more predictors and lead to overfitting. Similarly, polynomials can also lead to overfitting just because we can, and you can play around with this just for a simple case as well. The more polynomials are very nice tool, but they are very powerful and they can try to pick up all the noise and they can try to uh, fit to all the data points that are there if you keep on adding more and more higher polynomials. So be a little bit careful when you're using polynomial regression. So again, let's get on some hands-on experience. I'm going to go back to my single predictor just so that it's easier to interpret and easier to visualize. I'm using the same temperature as my x. Y is again same as ozone. I'm using a third degree polynomial here, and you can see the same results here. And the coefficient, the estimated coefficients are like x, x squared, x cubed. So these are the coefficient values. And as I mentioned, this one, there's a typo here, but the r squared has increased, as I mentioned earlier. For simple linear regression, it was 0.413, but now I have introduced a polynomial variable. It has gone up to 0.478. If I plot this third degree polynomial, so this is how this line looks like. It looks like it is fitting better than the linear regression, hence my r squared has increased, and it will probably be much better if I keep on adding more and more terms. But again, we have to be careful to not include each and every of them. Spline is similar to polynomial, but it's also another kind of non-linear ways of fitting predictor variables to the response variable. But it is done in a more piecewise manner and not just powers of x. It's more like I would fit, let's say I would fit from this point here to this point with this way, and then the next way will be another piecewise. So that's how spline works. You kind of divide it, we call it into knots. You kind of divide the whole point, like the whole data set into different points, and we call it as knots, and you can define what those knots are. You can specify them for the spline, and then the model will try to do, it will try to build up to that point itself instead of building up for the whole data set. Hope that makes sense. And I did the same thing again, defined my knots as 65, 75, 85, just some numbers I chose. And it gives me the coefficients for all of these points right now. So as I said, now it is trying to, as you can see, the number of predictors has increased, even though I specified only one X, but it is trying to, it has divided that up into these many points, and it is trying to estimate those values. And as a result of that, my R square also has gone up quite a bit compared to the simple linear model. And if I plot this, this is how my spline curve looks. As you see, it's trying to match all of these points up here, like trying to get a curve here, trying to get a curve there, instead of just a straight line. So yeah, that's all I have from my end. Always remember that regression has some limitations. They are extremely sensitive to outliers and influential values. And we have to always be careful of the assumptions of the linear regressions that we did. Like always check if the residuals are making sense, if they're independent, if they are normally distributed, and so on and so forth, before we just jump on to applying linear regression to everything. And with that, I will hand it over again to Sneha for some Q&A.
Awesome. Yes, we are 6 minutes before we could hit time. So let's take some Q&A before we conclude.
Sure.
Thank you, Madhurima, for this wonderful presentation.
Welcome.
Let me just open my Q&A.
Hope this helped. And
of course, it was wonderful. Yes.
And I'll try my best to answer questions. I see a lot of questions here.
Okay. Yes, there's a lot of questions. So the first question from Jasmine I would like to ask is on spline model, how do you choose the knot values?
That's a good question. So I would say definitely don't choose a knot value which is outside the range. Like, for example, I chose 65 because the range is somewhere like, let's say 55 to 100. So if I choose a knot value which is like 40s or 20s, it's not going to be able to interpret what that is just because it is not in the data range. So something within the data range would be the first to start with. So that's why I chose 65, 75, 85. So that's kind of within my entire data set. That's a good rule of thumb. Please don't choose anything like completely at one extreme versus another extreme. Like if you just use, like let's say 55, 60 and 65, this would only be doing the estimation towards one side. Same goes for the other side as well. So I would say a good rule of thumb would be to kind of cover the entire data set and have it maybe not always equally spaced, but that would be a good point to start and then play around and see where it goes, but not be too much on either end or very close to each other.
So here in this, when you say 65, 75, and 85 here, does that mean the lines needs to pass through those points? Is it a must? Is that what it means?
I think it, let's see. No, that's where I am defining my points or knots to be. It's think of it like how you distribute your data in a histogram, right? You bucket all those into bins. So I'm kind of think of it as binning my data set, and I'm kind of drawing a boundary like, okay, there should be a boundary at 65. There is kind of another bin which will range from 65 to 75, another bin which will range from 75 to 85. So think of it like that. It may try to pass it through those points, but let's see, does it? Yeah, it will try its best to pass it through those points just because you have defined them as your kind of bin boundaries, if you think of it that way.
Yep. This sounds good. That's a good one. And then now we will just go to the previous topics on outliers and influential
Sure.
values. So the first question is like, how do you differentiate outliers and influential values?
So an outlier is also an influential values. So it's not a different thing. So influential value is anything that will kind of influence your data in your model. So an outlier is definitely an influential value.
Um,
So to add to that, like if you, so these are the two charts that I showed earlier to identify influential values. And if you see like 62, 117, 121, they kind of come out here in my outliers as well, like 30, 62, 117. Similarly here in this chart and here in this chart as well. So outlier is like a subset, I would say, of influential values.
Yes, I agree. The other question is like, so we talked about linear regression, multiple linear regression, spline, and polynomial regression. Can you just briefly say like when to choose which one? Like go over like, how do you go from, okay, linear regression is what I want to use for this problem versus spline or polynomial for this other problem?
Yeah, that's a good question. So as I said, most real world problems are probably going to be multiple linear regression and not just a simple linear regression. So that's a very easy check. You can always start with one. If you have just one predictor, then yes, it will be simple linear regression. But if you see a lot more predictors, then multiple is the way I would start. And just because and it's just a warning for polynomial, as I was saying earlier, is that polynomial can give you a very nice, like you can get a very nice R squared value and it will be like, great, my model is working fine. But that has a tendency to go to do overfitting. So, and also it's always tricky to work with higher degree polynomials. So I would always start with multiple linear regression. And then if I see that, okay, this is not working at all, and I would probably need to go to maybe a quadratic equation instead of a simple linear one, then, sorry, multiple linear one, then I would go for that. Spline is a way to do polynomial. So unless and until I have not used spline like generally, unless and until it is a very specific scenario and I really want my data to fit, have all these strange curve and things like that, and I am trying to fit those. But otherwise, again, it's first of all, it's difficult to interpret. Like, how would you, if you want to explain how it becomes very difficult, like what does this spline from 65 to 75 mean? Like, what does that estimate tell you? It's one is it's difficult to interpret. Second is it may lead to overfitting. And I would just stick to multiple and then definitely do a regularization or a check for overfitting to see that I'm not doing something which I should not be doing.
Yes, I want to add to that of like most models, like you want to keep it simple, and usually regularization should solve it and make it powerful. It is very rare that we use polynomial and spline in the field. So that's something to add there. Thank you so much, Madhurima, for all this time. We had a wonderful time and there were so many amazing questions, and I see more questions in the Q&A. We will answer them as soon as possible. Like our volunteers are on it already. If not, you can reach out to any of us in Slack and we will try answering you that as well. And Madhurima, if you don't mind stopping this screen share, I would like to
take
Sure.
it forward.
Yep. Awesome. Thank you everyone for being present today and enjoying this wonderful presentation. We do have more lined up for you. So next week, we are doing statistics and classification, where we would talk about a lot of classification model, but from a statistics perspective. And it will be our speaker is Rishika Singh, and you all know her if you have attended any of our previous webinars. She's our Women Who Code data science lead as well. So it's on March 6th at 12 p.m. So I hope to see you all there. And next thing, make sure you join our Women Who Code Slack channels and be part of our community. We have a lot of member benefits like coding resources and a lot of other resources available for improving your data science skills. And lastly, I want to thank you all for your feedback, and we want to encourage you to discuss these topics in Slack as well. So join us and make sure you use this platform to ask any questions you might have. Our volunteers and our speakers are more than happy to answer your questions. Thank you for all your time, and hope you all have a wonderful weekend, and see you all next week. Thank you.